Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 2 of Algebraic Topology. So the main aim of this course is to study what is a category and what is a functor. So let's have a look what is roughly a category. So we'll be using category and functors throughout our course of Algebraic Topology. So this is a kind of language that we need to learn to understand the structures of algebraic topology. So let's see what is a category. To describe constructions of algebraic topology, we need notions of category and functors. So roughly speaking, a category is a collection of objects. So we discussed in lecture number 1 that a collection could be a set or could be a class as well. So for example, if we talk about collection of all sets, then it does not satisfy the axioms of sets, so it is a class. Similarly, collection of all topological spaces, collection of all groups, collection of all abelian groups, so they form a class and not a set. So this collection of objects, so in most of the cases it's a class and not a set. So this collection could be any collection of objects. So for example, it could be collection of all vector spaces. So, okay, so objects of category could be all vector spaces, all vector spaces over the field F. Similarly, we can study the objects of abelian groups, so all abelian groups. And next, we can also discuss a category where the objects are, for example, rings. And similarly, we can take other objects as well. So that's our first component of the category. So what is the second component? So with these objects, we require morphisms between the objects, and we denote set of all morphisms from the object A to B by hom AB. So for example, if A and B are two elements of the objects of this category, then set of all morphisms from A to B is denoted by hom AB. So if A and B are groups, and we are discussing the category of groups, for example, so we denote the category of groups by groups. So the objects of the category named groups is all groups. So in this case, if I take two elements A and B from this category, and A and B are elements or objects of this category, then set of all morphisms from A to B is denoted by hom AB. We have also seen in lecture number 1 that collection of all morphisms, homomorphisms from set A to B, or in particular group A to B, is denoted by hom AB. But this notation is not restricted to groups only. So for example, if we are considering the category of all topological spaces denoted by TOP, top, so the objects are topological spaces. So let's say T1 or T2 are two topological spaces, then the set of all morphisms between T1 and T2 is denoted by hom T1 to T2. But when we are considering topological spaces, then the morphisms are basically continuous maps. So basically in this case, hom T1 to T2 is morphisms from T1 to T2, or basically set of all continuous functions from T1 to T2. Of course, if we are considering topological spaces, then there is no homomorphism between the topological spaces. So here the word morphism means so the concerned morphism of the objects. So if we are having topological spaces, then these morphisms are continuous maps. So basically this is equal to continuous maps F from T1 to T2. So collection of all continuous maps from T1 to T2. Okay, so that's our second element in the category. So far we have studied two objects that are part of the definition of category. So first we need objects, and second we need morphisms between the objects. And the third component is we should be able to take composition of these mappings. So for example, if I have a function from A to B, so A and B are of course objects of the category, and if I have another map from B to C, and B and C are elements of the objects of the category, then I should be able to define what is composition. Okay, so of course we can define composition in many different ways, but if we are defining a category, then we also fix, so apart from fixing what are objects and what are the morphisms from any two objects, we also fix that how we are going to take composition of two functions. Of course I can't take composition if G is a function from some other set, let's say D to C. So in this case composition is not possible unless there is a relation between B and D, but in this case composition is possible. So whenever it's possible, then I also define how to compose two functions. So we have three components of the definition of the category now. I should have objects, I should have morphisms, I should have the rule to define composition. So for example, let's take the category of topological spaces. So we have objects as set of all topological spaces, and home from A to B is set of all continuous functions from A to B. And similarly we can consider the category of abelian groups. So in this case the objects of the category are all abelian groups, homomorphisms are all homomorphisms. Okay, so in this case this home A to B, which is a set of all morphisms from A to B, is the collection of all homomorphisms, because in the case of groups morphism is in fact homomorphism. In the case of topological spaces, morphisms are in fact continuous functions. Okay, so as we change the objects, the morphism changes. So we shall study these categories more closely later in our discussion. So once again this is a rough definition of the category. Precise definition is coming in few slides, but roughly speaking it's collection of three components. I should have objects, I should have morphisms, I should have a rule how to define composition. So what is a functor, roughly speaking? So functor is basically a function between the two categories. Of course a category consists of three components: objects, morphisms and compositions. So I should be able to give images of all these three components if I am defining a function from a category C to a category D. So let's see an example of a functor. So consider this homology functor. So we can just consider this as a function from this category of topological spaces to the category of groups. So this functor, what this functor does is it takes topological spaces and it gives me abelian groups. So basically if X is any object of top, or in other words is any topological spaces, then H and X is an abelian group for every X belongs to the objects of this category. Now that's how we take images of the objects, but it's a functor between the categories, and category has three components. It has objects, it has morphisms and it has compositions. So it should also be able to give me images of the morphisms as well. So for example, in this case the morphisms are continuous functions. So if f is any continuous function from x to y, then we have this image Hn of f, which is basically a function from this abelian group to this abelian group. So now it's going to be a morphism between these two abelian groups. So what is a morphism in the case of groups? So this is homomorphism. So Hnf is basically a homomorphism from this abelian group Hn of x to Hn of y. So for example, if f is a continuous function from x to y, then Hnx to Hny, we have this function. So what about the composition? So if we have a function f and we have a function g, of course continuous function. So if f is a function from x to y and g is a function from, let's say, y to z, then we can take the composition f and then composed with g. Then what does this homology functor does with the composition? So as we have seen that it takes x to Hn of x, y to Hn of y, and f to Hn of f. And similarly for g, it will take g to Hn of g, and it will take z to this abelian group Hn of z. So we can see that we will first compose this homomorphism with this homomorphism. So that's how it gives me images of the composition. So now we have images of three components of the category. We know how to take images of the objects, we know how to take images of the morphisms, which are continuous function in this case. We know how to take images of the composition. So these three essential components have been mapped from one category to the other category. So that's what roughly a functor is. Okay, so similarly it also takes the identity function from the category of topological spaces, and it takes Hn of x to Hn of x. So for example, if we have identity function between the topological space x and x, then under this function or under this functor, this identity map is mapped to the identity of these abelian groups. So Hn of x to Hn of x. So we will see in detail and in precise way what is a functor, but this is what roughly a functor does. So let's define precisely what is a category. As we have seen earlier, that a category has three components. It has objects, it has morphisms, and this morphism is a generic word, and for example, if we are taking objects to be groups, then these morphisms are homomorphisms. If these objects are topological spaces, then these morphisms are continuous maps. If these objects are, for example, sets, then these morphisms could be simple functions as well. And the third essential part of the definition of category is we should have a rule of composing two functions. So basically there should be a function from home AB cross home BC to home AC. So if I have a function from A to B, and if I have a function G from B to C, then there should be a rule of defining F composition G, and of course F composition G is a function from A to C. So this rule is also the third component and essential component of the definition of category. So there are some conditions that these three components should satisfy. So the first thing is the family is well defined and is the elements of home AB is pairwise disjoint. So secondly, composition is associative when defined. So in other words, this means that the composition should satisfy the following condition. So in other words, we should be able to write down composition without brackets. Okay, so I can compose these three functions in any way and the answer will be the same. So when defined, of course, the composition is defined. For example, if f is a function from x to y and g is a function from y to z and h is a function from z to, let's say, k, then this composition is defined. And of course, if h is a function from some other set a to k, then the composition is not defined unless there is a relationship between a and z. So whenever this composition is defined, then this is associative. So the next condition is that for each object A belongs to the objects of the category, there exists an identity in this set of morphisms from A to A. So satisfying the following condition, if I have f from B to A, and if I start from f and compose it with the identity of A, then this composition is nothing but f. So if I start from this set B and take its image under f and then apply this element 1a, then this is the same as f of b. Similarly, the next condition is, if I have a map from A to C, which is g function, then if I first apply the identity on some element of A and then apply g on that element, then this is the same as applying g on element of A. So that's our third condition. So if these three conditions are satisfied, then we say that it is a category. So once again, let's see what is a category. It has three components: objects, morphisms, and composition. So satisfying the following three conditions, so it should be the elements of the morphism should be pairwise disjoint, composition should be associative, and there should be identity maps or identity morphisms as well, satisfying these two conditions. So there is a simple remark that sometimes we write f from A to B instead of f belongs to home A to B. So let's consider examples. So starting from a very simple example of the category of sets. So in this case, what are the objects? All sets. So once again, objects of this category does not form a set, so it's a class. So the elements are set of all sets. So in case of we have objects to be sets, so in this case the morphisms between two sets is just a simple function. So as I have said earlier that the definition of the morphism depends really on the objects. So in case of sets, we take morphisms to be just simple functions. And the third component of this category is the composition, and we take composition to be the usual composition of functions. So for example, if we have function g from the set R to R defined by g of x is equal to x square, and if we have another function f from R to R defined by f of x is equal to sine x, then the usual composition f circle g of x is basically f of g of x. And then what is g of x? G of x is x square, so we replace g of x with x square. So what is f of x square? So f of x is sine x, so just replace this x with x square. So that's how we compose any two functions. So in this case these functions are between the sets R and R. So let's see what is a subcategory. So if I have two categories C and A, such that all the objects of the category C are also objects of the category A. In other words, object C is subset of objects of A. And if AB belongs to the objects of C, then we denote the two possible home sets by this. So see that in the definition of the category we have three components: objects, morphisms, and the composition. So it's up to us to take objects to be any objects as long as they are satisfying the definition of the category. So similarly, we can take morphisms to be any set of morphisms, once again, as long as they are satisfying the definition of the category. And similarly, we can define composition to be any rule that satisfies the definition of the category. So in other words, if I am taking a category C and a category A, then they have the same objects, because set of objects of C is subset of objects of A. So if A, B are objects of C, then of course there are also elements of the objects of A. But the morphisms between A and B in the category C could be different than the morphisms between A and B in the category A. So once again, they could be, in general, they are different, and of course they satisfy the definition of the category. So since the objects are the same but their categories are different, and therefore they are different sets, so they are different sets of morphism in general. So that's why we denote the home set between A and B in the category C. So we mention this small subscript of C if we are taking the morphisms between A and B in the category C. And if we are taking the morphisms between A and B in the category A, then we denote it by home A to B with this subscript cap A. So what is a subcategory? So C and A be categories, and the objects of C are contained in the objects of A. Then C is a subcategory of A is if the homomorphism between A and B in the category C is subset of the homomorphism between A and B in the category A, for all A, B belongs to the objects of C. So not only the objects are subsets, but also the morphisms between any two objects. And the composition in C is the same as the composition in A, that is, the function is restriction of the following composition function. So of course in the category we have as a third component the composition rule. So we are saying that in the subcategory the composition rule is the same as the composition rule in the category, but of course since we know that this set which is the set of morphisms from A to B in the category C is subset, so this is subset of this set, and similarly this set is subset of this set, and this set is subset of this set. So this composition is definitely restriction of this composition. So the elements which will be here, so for example, if I have F1 up to Fn elements, then some of these elements may not be in this set. So the composition rule is the same, but it has been restricted, so we are ignoring some function somehow. So this composition rule should be the same in the subcategory. So once again, three components are there in the category. So if we are defining a subcategory, then all these three components should be some sort of subsets in this sense. So objects should be subsets of the objects, morphisms should be subsets of the morphisms, and the composition should also be the same. So consider the category of topological spaces. So in this case the objects are all topological spaces, and of course it's a class. And what are the morphisms? So in the case of topological spaces, morphisms are continuous functions from A to B, and composition is usual composition, just like we have defined in the earlier cases. So the category top has many interesting subcategories. For example, the category of compact topological spaces denoted by C top. So this notation C top is not a very standard notation. So the objects, of course every compact topological space is also a topological space. So of course we can observe that the objects of C top is subset of object top. So the objects of the category of topological spaces. Similarly, home A to B, all continuous function from A to B. Okay, so if we have a compact topological space, then it is also a topological space, and if I have two compact topological spaces, then there are also topological spaces, and the home between them is the same in the case of this. So the home between A and B in the category of C top is equal to the home in the category of top A to B. So in this case, this is also a subset of this, so in particular they are equal. So we are taking composition to be usual composition, so once again they are the same. So by definition of the subcategory, the set of or the category of compact topological space is subcategory of the topological spaces. So similarly, we can construct other subcategories of the category of topological spaces by considering the objects to be, for example, Hausdorff spaces, subspaces of Euclidean spaces, etc. Or we may consider subcategory by keeping the objects to be the same and restricting the mappings to be differentiable. So let's go back to our calculation. So in this case, we have restricted the objects. So observe that the morphisms remains the same. So there is equality in the morphisms because they are just continuous maps. So instead of just restricting the objects, we can just keep the objects and restrict these morphisms. So for example, let's consider another category, let's say C prime. Take its objects to be objects of the topological spaces, and take home from A to B for any two objects in this category C prime. So take them to be all differentiable functions. From A to B, and take the composition to be usual composition. Composition is usual composition. So this is the category C prime. So let's relate this category C prime with the category of topological spaces. So in this case, the objects are the same as the objects of the category of topological spaces, but so we have restricted these morphisms. So in the case of topological spaces, the morphisms are all continuous functions from A to B, but in this case we have restricted them to all differentiable functions from A to B. So this is essentially a subset, because we know that every differentiable function is continuous from calculus. So this is subset of home in the category of topological spaces from A to B. So in this set we will also have functions which are continuous but not differentiable, but in this case we have only differentiable functions. Of course, every differentiable function is continuous. So this set of morphism is subset of this set of morphism, and composition is usual composition, so there is no problem with the composition. So instead of restricting the objects, we can also restrict the morphisms, and then we obtain new subcategories of the given category. Let's consider another example of the category of groups. So in the category of groups, objects are groups and the morphisms are all homomorphisms. Okay, so we can also restrict this thing. So it's not necessary that we should take all homomorphisms. So it depends on situation to situation. So in this example we have taken them morphisms to be all homomorphisms. So of course it's our choice, as long as they are satisfying the axioms or the conditions of the category, we can take this set to be any set of morphisms. Okay, so in this case we have taken home A to B to be the set of all homomorphisms from A to B, and the composition is usual composition. So an important subcategory of the category of groups is the category of abelian groups, and we denote it by AB. So these notations, so denoting the category of groups by groups bold letters and the category of abelian groups with AB bold letters, it's very standard notation. So in this case, what are the objects? So the objects are all abelian groups, and the morphisms are all homomorphisms from A to B, and composition is usual composition. So observe that the objects of AB, of course, is subset of the objects of the groups. So every abelian group is a group, but of course converse is not true. So this is contained in this. But in this case, if we have two abelian groups, then home A to B in the category of abelian group is the same as home A to B in the category of groups. So in this case there is no change. Similarly, composition is the same as usual composition. So by the definition of subcategory, the category of abelian group is a subcategory of groups. So let's consider a relatively non-trivial example. So consider the category of pairs of topological spaces. So what are the objects? So the objects are all ordered pairs XA, where X is a topological space and A is a subspace of X. Okay, so a morphism from XA to XB is an ordered pair FF prime, where F from X to Y is continuous, and this relation is satisfied where I and J are inclusions. So in other words, what we are saying is it's just going to be a continuous map from X to Y, and since A is subset of X, so there is inclusion from A to X, and B is subspace of Y, so there is inclusion from B to Y. So this map is basically F prime. So pictorially we can say that F is a continuous function from X to Y, and when we restrict this F to A, then F of A is contained in B. Okay, so we are taking continuous functions between the topological spaces with an extra condition that F of A is contained in B. So that's what it means to be a morphism between two pairs. So F is a continuous function from X to Y, and F of A is contained in B. So composition is coordinate wise. So that's how we define the three components of the category. So what are the objects? Objects are the pairs. So pairs where one coordinate is basically a topological space and the second one is a subspace of X. And how to define morphisms between them? We define continuous function from X to Y, and F of A is contained in B, and composition is coordinate wise. So there is an important subcategory of the category of pairs of topological spaces. So in this category, instead of taking a subspace of the topological space, we just take a point from this topological space X. Okay, so how to define morphism? So let's go back and see the condition. So F should just be a continuous function from X to Y such that F of A is contained in B. So in this case, our subspaces are just points. So we can just say that F is a morphism from X to Y such that, so this X naught is contained in X, so there is inclusion map, and this Y naught is contained in Y, so there is inclusion map from this set, and this is the map F prime. So in other words, we can just say that F of X naught should be equal to Y naught. So this diagram says that if I start from X naught, take its image into X, so this is inclusion, so I of X naught is basically an element of X. Apply F on this, then I will get an element. Similarly, if I apply F prime on this and then restrict it to y, or take its image under j into y, then these two images should be the same. So in other words, we are just requiring that f of x naught is equal to y naught. Okay, so this is an important subcategory of the category of pairs. So this morphism is also called pointed map or base point preserving map. So x naught, and so we can just say that x naught is base point of x and y naught is base point of y. So base point just means a point which is fixed. Okay, of course we have fixed x naught inside x, and similarly y naught is fixed in y. So we are calling them base points. Of course there are some reasons for calling them to be base points, which will come in the later discussion. So diagram, what is a commutative diagram and what is a diagram? So a diagram in a category C is a directed graph whose vertices are labeled by the objects of C and whose edges are labeled by morphisms in C. So for example, if we have the category of top, category of all topological spaces, then consider this graph x1, x2, x3, x4, x5. So these are the vertices, and the edges should be directed. Okay, so consider this. So we can add more vertices if we want. So similarly this. So this is a diagram in a category of topological spaces. So in this case, these xi's are topological spaces, and basically these maps, so let's say this map is f14, f145, f15, f13, f16, f32, f36, f67. So all these fij's are basically elements of the morphisms. So these are morphisms between the topological spaces. In other words, these are all continuous maps. So fij's are continuous functions. So this is a diagram. A commutative diagram in C is a diagram in which for each pair of vertices, every two paths between them are equal as morphisms. So we have already seen an example of a commutative diagram. So when we were discussing the category of pairs of topological spaces, so we discussed that if F is a morphism between the two pairs, so X is topological space, A is a subspace of X, and this morphism is from XA to YB. Once again, Y is a topological space, B is a subspace of Y. Then this map is basically a map such that it satisfies the following condition. So A is a subspace of X, so there is an inclusion map. So basically it's a very simple idea. So for example, if Z is set of integers and R is set of real numbers, then of course Z is contained in R. We can also say that there is a function from Z to R, and of course this function is I of Z for any integer is equal to Z. So this is inclusion function from Z to R, and sometimes we denote it with this arrow I. Okay, so I from Z to R. So this curly arrow means that this Z is contained in R, so this is inclusion map from Z to R. So this A is contained in X, so there is inclusion map from A to X. Similarly, there is inclusion map from B to Y because B is subspace of Y. So the following condition is satisfied. So F should be a continuous function from X to Y such that So this map is I, and this map is J, and this map is F prime, this map is F. So the diagram is commutative and denoted by writing down this curly arrow inside the diagram. So diagram is commutative means if I start from this A and end up at this Y, and if I choose any of the paths, then there will be no difference. So there is commutativity in the diagram. Or if I start from A and choose any path to reach Y, then there will be no difference in the image. So for example, if I first apply I and then apply F, then of course on some element of A, then it is the same as first applying F prime on that element and then applying J on that element. Okay, so it is the commutativity of the diagram. Okay, so a commutative diagram is a diagram in which for each pair of vertices every two paths between them are equal as morphisms. So this path and this path, so they are equal as morphisms. So that's why it's a commutative diagram. A congruence on a category C is an equivalence relation on the class of all morphisms in C such that the following conditions are satisfied. So what is an equivalence relation? So we have already discussed this in our first lecture. So now we are taking an equivalence relation on the class of all morphisms. So we are taking union of all morphisms A and B, and these A and B belongs to the objects, of course. So this belongs to objects of the category C cross objects of the category C. So these A, B are elements of objects of the category C cross objects of the category C. So it's an equivalence relation on this set satisfying certain properties. So what are the properties that it must satisfy? So if F is any morphism from A to B and F is equivalent to F prime, so this equivalence definitely means that under this equivalence relation. Okay, so if F is equivalent to any other morphism, then F prime must also belongs to this set home A to B. So this is our first condition. The second condition is if F is equivalent to F prime and G is equivalent to G prime and the composition G circle F exists. So whenever we say composition exists, it means that it satisfies the condition that F is a function from A to B and G is a function from B to C. Of course we can't take composition if G is not a function from G to C, and for example if G is a function from some set Z to C, then we can't take composition. So if it exists, then it implies that G circle F is equivalent to G prime circle F prime. So these two compositions are equivalent as well. So of course equivalence relation has three properties that it must satisfy, but we impose extra conditions on this equivalence relation. So if these two conditions are satisfied, then we say that we have a congruence on the category C. So let C be a category with congruence this, and F denote the equivalence class of a morphism, and define C prime as follows. We define another category from this congruence, and the objects of C prime are the same as objects of C, but we restrict some sort of restriction is there on the C prime. So how do we restrict? Because we are taking morphisms from A to B to be the classes of morphisms and not just elements. So a class of elements, so for example F is a morphism from A to B and we are considering its class. So its class in general will have many elements, and of course we can represent this class by any of the elements, but in general, so let's say if the class of F has elements F, F1 up to Fn, then we represent this class by F, and it's just one element in this new category C prime, and instead of n plus 1 elements, it's just one element in this set of morphisms from A to B. So basically we are some sort of restricting the morphisms from A to B. And similarly, how do we define the composition? So composition of these two classes defined as just take the class of the composition of G circle F. So now this C prime is a category. So the proof is given here, and the proof will also be provided in the lecture notes, but it's just an exercise to show that it's a category. So it satisfies all the properties of the category. Of course, it has objects, it has morphisms, and it has a rule for composition, and the only thing we need to check that it satisfies the three conditions that we imposed on these three objects. So the category C prime just considered or just constructed is called a quotient category of C prime. One usually denotes home C prime A to B by AB bracket. Let's consider an example. Let C be a category of groups that we denote by groups, and let F prime belongs to the homomorphism from G to H. Define F is related to F prime if there exists A belongs to H with F of X is equal to A F prime of X A inverse for all X belongs to G. Okay, so basically F is a function, or in this case, because the objects are groups, so it's a homomorphism from G to H. Similarly, there is another function F prime from G to H, because they both belong to home G to H. So we say that these two homomorphisms are equivalent if there exist. So if there exist A belongs to H such that F of X is the same as A F prime of X A inverse for all X belong to G. So in other words, if this relation is satisfied, then we say that F is related to F prime. So it is routine to check that this is an equivalence relation on this set. Okay. So similarly, we can define a home on other sets, and then we can take the union. So let's go back to the congruence definition. So I should have an equivalence relation on this set. So what is an equivalence relation? So an equivalence relation is a relation which is reflexive, which is symmetric, and thirdly which is transitive. So in other words, in this case I need to check that F is related to F or not, number one. Number two, I need to check that if F is related to G, then this implies G is related to F, and thirdly I need to check that if F is related to G and G is related to H, then F is related to H. So the third condition that I need to check is F is related to G, G is related to H, then F is related to H. So why F is related to F? Because in this case I can take this A to be just identity of H. So F of X is equal to identity F of X, identity inverse is identity, so F of X is equal to F of X. So F of X is related to F of X. Similarly, if F is related to G, which means F of X is equal to A G of X A inverse, so I can just consider G of X to be A inverse F of X A. So as we can see that there exists another element, and this new element is A inverse. So in this case the element is A, and in this case the element is A inverse. So F is related to G implies G is related to F. So it is symmetric as well, and similarly we can show this last but most complicated condition of these three, that if F is related to G and G is related to H, then F is related to H. So if this relation satisfies these three conditions, so it is an equivalence relation. So we have an equivalence relation on the collection of all morphisms of these category. So now to see that this is congruence relation, assume that F is related to F prime and G is related to G prime, and that G circle F exists. Okay, so what do we need to check now? So let's go back to the definition and see what do we need to check here. So we need to check that if F is related to F prime and G is related to G prime, then the composition G prime, and if the composition exists, then G circle F is related to G prime circle F prime. Okay, so this is an equivalence relation on the set of all morphisms of this category. Now let's see the definition of the congruence, and let's see what we need to show here. So the first condition is if F belongs to home A to B and F is related to F prime, implies F prime belongs to home A to B. So this is very simple, because if F is related to F prime, so we have seen here if F is related to G, then G is related to F, and if F is a morphism from A to B, then F prime is also a morphism from A to B. So this condition is very simple to see. So the next condition that we need to show is that if F is related to F prime and G is related to G prime, then the composition G circle F is related to G prime circle F prime. So basically what we need to show here is that G circle F is related to G prime circle F prime. Okay, so let's start from G of F of X. So how do we define F of X? So F of X is basically equal to A F prime of X, A inverse. So let's replace this in place of F of X, F prime of X, A inverse. So G is a homomorphism. So according to the definition of homomorphism, this should be equal to G of A, G of F prime of X, and G of A inverse. So now what is G of F prime of X? So using this definition we can see that G of A, so B G prime of F prime of X and B inverse and G of A inverse. So now from the group theory we know that G of A inverse is equal to G of whole inverse. So basically G of A inverse is equal to the inverse of G of A. So G of A, B is one element, G prime of F prime of X, and then so G of A whole inverse multiplied by B inverse. So this is basically equal to G of A B whole inverse. So we can write it down as G of A B whole inverse. So this is the same expression as this expression. So what is G of A? So basically G of A is an element of K. So we can see that G is a homomorphism from H to K. So G is a homomorphism from H to K. So G of A is an element of K. B is also an element of K. So we can say that G of A into B is an element of K. Similarly, G of A into B inverse is also an element of K, because K is a group. So it has an inverse. So G of A into B inverse is also element of K. So basically we can say from here that g of f of x is equal to this element, or in other words, so this function is basically g circle f, and this function in the middle is basically g prime circle f prime. So we can say that these are equivalent function because this function is equal to some element of k, g prime composition f prime, and the inverse of the same element. So we can say that this will define a congruence on the category C. So thus the quotient category is defined if G and H are groups, then GH is the set of all conjugacy classes F, where F from G to H is a homomorphism. So as I've said earlier that if C is a category, then after defining a congruence on the category, we can define this category C prime where the objects of the category are the same. So basically objects of C are the same as objects of C prime, but the homomorphisms are different. So in the case of C prime, the home C prime from A to B is the set of classes, is the set of equivalence classes, so where F belongs to home in the category of C from A to B. So after restricting these morphisms, so this is our new category C prime, and this is the quotient category of C. So the most important quotient category for us is the homotopy category, which we will discuss in our next discussions. So let's come to our next important concept of the lecture. So if A and C are categories, a functor T from A to C is a function that gives me images of elements which are elements of objects of the category. So it will give me images of objects. Also, if I have a function from A to A prime, which is a morphism in this category A, then it will give me functions TF from TA to TA prime. Okay, so if F and G are morphisms in A for which G circle F is defined, then we can also give image of this composition, and image of this composition is defined as the following. So a category has three main components: objects, morphisms, and composition. So a functor will give me images of the objects, it will give me images of the morphisms, and it will give me also how to give image of the composition. And also it will take identity elements to the identity elements. So for example, if 1A is identity from A to A, then this functor 1A will take so basically this TA is image of this A under this functor T, so this TA, so this is also identity. Okay, so such functors are called covariant functors because the direction of arrows in the morphisms remain the same. So if we have a morphism F from A to B or A to A prime, then TF is also a morphism from TA to TA prime. So in this case you can notice that A to A prime and TA to TA prime, so the T does not change the direction of the arrows. If it's from A to A prime, then it will be from TA to TA prime. So the direction of the arrow is not changed, so basically it's a covariant functor. So we can define another type of functors called contravariant functor. So everything else remains the same except for the case that in this case, if F is a morphism from A to A prime, then SF, so in this case small f, SF will be a morphism from SA prime to SA. So in this case notice that if we have a morphism F from A to A prime, then SF is a morphism from SA prime to SA. So notice that the arrow is reversed. So A prime is now here and A is now here. So the arrow is reversed, so that's why this is contravariant functor. And similarly we will define the composition in the following way. So if F is a morphism from A to A prime, and G is a morphism from, let's say, A prime to B. So basically we can define this composition G circle F in this case. So since SF is now a map from SA prime to SA, so now SF, so this map is basically SF is a morphism from SA prime to SA, and similarly SG is a map or morphism from SB to SA prime. So that's why we will start from SG and then compose it with SF. So you can see that the ordering of these G and F has been interchanged. So G circle F goes to F circle G. So similarly the last condition is the same, identities should go to identities. So this is how we define contravariant functor. So let C be a category and B belongs to C, be a fixed object. So consider a functor home. So how we define this functor from the category to the category of sets? So if any object A is given, then this object A is taken to home A to B. So that's how we define images of the objects of the category C. And each morphism G, of course, if it's a functor, then I need to give the image of the morphism as well. So for each morphism G from A to A prime, so we define the following image. Okay, so home G B, which we can also denote by G upper star. So how do we define this G upper star, which is the image of G under this home functor? So it will give me a function from home A prime B to home A B. So if I have, for example, a function H from A prime to B, then this image G upper star will give me a function from A to B. So what is this G? So G is a function from A to A prime. So G is a function from A to A prime. So we start from A, goes to A prime, and this H is a function from H prime to B, and we have taken this H to be an element of home A prime B. So this G composition H is a function. So if I start from A, apply G first and then apply H, then it's a function from A to B. And composition of morphisms is a morphism. So basically this G composition H is a function from A to B. So G composition H is an element of home A to B. So we can say that this functor takes morphisms from A to A prime and gives me morphisms from A to B. So this is the function of this G upper star. So next example, let C be a category of all finite dimensional vector spaces over a field F. Then we define the following functor. So in the previous example, we have taken this B to be a fixed element of the category. So notice that we have also done the same thing in this example. So since F is a vector space over itself, so F is a vector space over F, so that's why this is an element of the category of the set of all finite dimensional vector spaces. So that's how we are defining this functor. So basically we have taken that B and we have replaced that B instead of F, and so once again this is a contravariant functor, and this F upper star is defined in the similar way. So an equivalence in a category is a morphism F from A to B for which there exists a morphism G from B to A such that their composition is identity. So if A and C are categories and T from A to C is a functor of either variance, so either variance means it could be a contravariant functor or it could be a covariant functor, but in both cases TF is also an equivalence in C. So the proof of this theorem has been excluded from this course. So the last definition of this lecture is an important one, the forgetful functor. So what is a forgetful functor? So it takes structures and it forgets. So as the name of this functor suggests, that it is forgetting something. So it forgets the structure of the objects, and it forgets the structure of the morphisms as well. So for example, if f is a forgetful functor from top to sets, then it will take topological spaces and it will forget that these are topological spaces. So for example, if we have a topological space 1, 2, 3 with open sets, let's say just the singletons 1, 2, 3 and x and phi, then it will forget this tau part, and this x tau topological space under this functor f will just be mapped to the set X, which is just the set 1, 2, 3. So it is forgetting this topological structure of this topology. Similarly, if we are taking groups and you are defining a forgetful functor, then it will forget the group structure of these groups. So for example, if f is a functor from the category of groups to the category of sets, and let's say we have S3, the group which is 1 x y xy xy square y square. So this is the group S3. So now we know that we can multiply these elements. There are also identity elements, there are also inverses of every element. We can also calculate the order of an element, and we can do the group operation with these elements. But when we apply this forgetful functor on this object S3, which is the object of the category of groups, then I will just get a set 1x y. So the elements are going to be the same, but I don't know what does xy mean here, or what does xy into xy square mean here. So here it doesn't make sense. So does not make sense. So here it makes sense. Here I can multiply xy and xy square, and the answer will be one of these elements. But when I apply the forgetful functor on this group, I just get a set, and there is no group structure on this set. So that's what forgetful functor does, and similarly it does to the morphisms as well. So it forgets the group structure and any other structure which is present in the category. So this is the end of the lecture. Thank you very much.